electronegativity, okay, affinities, okay, as well as the atomic radii. And we learn also about the size, the atomic size between molecules or what is it, already between the metallic radius, okay, covalent radius as well as ionic radius. And what else we learned? I think that's all I think we learned last time. So for these ones, we're gonna continue. Okay, mostly we will cover about the primary bonds as well as the secondary bonds. So I think all of you already learned this about this topic about the primary bonds and also secondary bonds. So I would like to ask you what is the chemical bond actually, or the atomic bonding? Anyone? And what is the goal of the chemical bonding? Anyone can answer, or maybe if you don't want to talk, you can write in the chat. Okay, in the chat box. Okay, can you give any suggestion? What is the chemical bonding? What is the chemical bonding goals actually? Or you want to use Padlet? You can write in the Padlet. Wait, okay. I give you the to attain stability. Yes. Good. So okay. Attraction between atoms. Yes. Okay. Attraction force between atoms. Okay. Good. What else? Lukman Hakim. So what is the goal actually? Oh, the goal is attain stability. Okay. Yes. Stable compound. Okay. So what I would like to explain here is okay. The chemical bond is actually to attract force between atoms and cause a multiple atom to come together. So they will bond together. Okay. So the goal is to get the stable compounds or based on the octet rules. Okay. And generally the octet rule states the outermost energy level of each atoms to have 8 electrons. Okay. I think all of you already know. And when the rule is satisfied, so your compound is stable. So that's the goals, and also the definition about the chemical bond. Okay, so this is a type of bondings. Okay, uh, which is divided into two. Okay, one is the primary bonds, and the second one is secondary bonds. Okay, and the chemical bonds for the primary have three types, which is ionics, generally for metal non-metals. Covalent is non-metal non-metal, as well as metallic is metal metals. But metallic is not really the bondings. Is mostly like the sea of electron itself. Okay, between metal and metals. And secondary bonds is a physical bond, but it's not actually linked together. It's more to like interactions, the outer of the electrons. So that's why it's a secondary bond. Okay, for example, like hydrogen bonds. Okay, van der Waals. Okay, can be divided into two, fluctuating dipoles as well as permanent dipoles. Okay. So ionic bondings. Okay, this is the definition. Okay, strong electrostatic attraction. Okay, between oppositely charged particles. Okay, because they will transfer the electron, and another atom will accept the electrons. Okay, so one electron which is give the electrons is going to be cations, and the accept electron is going to be anions. Okay, so for the covalent bonds, okay, pair of electrons that are more or less evenly shared between two non-metal atoms. Okay, large interactive force. And metallic bonds is non-directional bonds. Okay, is a sharing of electron between metal atoms. Okay, mostly on the we call it a sea of electrons. Okay, and permanent dipole is a weak intermolecular bonds due to attraction between the end of permanent dipoles, whereas fluctuating dipole is a very weak electric dipoles. Okay. is a temporary. Okay, so like a van der Waals is a temporary. Okay, so the driving force. Okay, as I told you that primary bondings, okay, to achieve the stable state of or octet rules, okay, by bonding with other atoms to transfer or sharing valence electrons, okay, and secondary bonds, secondary bonding is very low energy, okay, and the driving force is the attraction of electric dipoles containing atom or molecules. For example, hydrogen bonding, right? H and O. So there has a electric dipoles. Okay, so let's see the primary bonds. Okay, this is a three model of chemical bonding. Okay, ionic bondings, covalent bonding, as well as metallic bondings. This is what I told you that the electron is transferred to the, for example, this one Na and Cl, right? Electron transfer from Na and give it to Cl. Cl accept the electrons. Okay, this one is the sharings for the covalent bonding. Whereas this one Na, okay, the metals, okay, the metals ion cost in the electron C, okay, the C of electron. Okay, this is the difference. Okay, so let's see the ion bonding formation. So if you look at here, we can form the ionic bondings between group of 1A to A, or alkali and alkali metals, with group of 6A and 7A. 6A, 7A like a Cl. Okay, Br is a good what is it? If you do the synthesis, this is a very good group. The living group is good living group actually. Okay, group like a BrCl is a good living group. Okay, and when the metal loses electron, a form of cation. Okay, so the radius is gonna be reduced. You have to remember that. And the atom or group 6A, 7A, okay, reactive nonmetals, when gains these electrons, is gonna be an ion. So the radius is gonna be increased. Okay, so these ion are bound together by Coulomb attraction force. Okay, so it's called as ionic bonding. This is very strong. Generally, in terms of the electronegativity, okay, if the electronegativity difference, generally we measure from 0 to 4, right? So if there is a electronegativity difference between 0.5 to around until reach 2, we call it as a covalent bonding, but it's more than 2 is ionic bonding. Okay, so I will explain later about this range. Okay. Okay, so usually 0.0.5 is a non-polar bonding. Okay, so if you want to measure the electronegativity difference, you can refer to the periodic tables. Okay, usually on the right side of the periodic tables, measure number 4. Okay, and then on the left is between 0 to 0.5. Okay, so this is the example of an ACLs. Okay, sodiums, okay, is transfer electrons, okay, 3s1 to the chlorines. So if you can see here that the radius, right, the radius is the size is reduced. Okay, this is reduced, and this one is increased. Okay, because it's gain electron. So you have to remember this one. Okay. Okay, so actually, how for the ionic bondings, we can represent in three not methods but three ways. Okay, electron configurations, orbital diagrams, as well as Lewis electron dot symbols. Okay, do you know what is the electron configuration? If you remember, electron configuration is something like this. Okay. The last time when we do together the tutorials about the electron configuration, right? For example, 1s2, okay, 2s2. This is a electron configuration. Okay, 2p6. This one in term of electron configuration. This one you have to know. Okay. So in term of orbital diagrams, this one is a electron configuration. Okay. Configuration. Orbital diagrams. Okay. This one in term of orbital diagram is, you remember, based on the Hans rules. Okay. Okay. one, wait, one, for example, lithium. Okay, one, for example, lithium, right? This one is three. Okay. This one in terms of orbital diagram. Okay. Okay. So in terms of what is it? Lewis E dot symbol. Okay, you can present in terms of Lewis symbol. Okay. Okay, for lithium. Okay. This one is Lewis. Okay. You have to remember that. This one is Lewis symbol. For example, lithium and ferrum. Okay. This one if lithium and ferrums. Okay. This one transfer electron here. Okay. So this one you have to know. Okay. So lithium become plus F off. This is basic in chemistry. In chemistry also, I think you will learn this one. Right. This symbol. Okay. How about this one? Orbital diagram. If for orbital diagrams, okay, this one is 1s, 2s. This one is 2p for lithium. Okay, lithium and ferrum. Okay. While for fluorine, not ferrum. Sorry. Okay. This one orbital diagram, right? So must be follow the Hans rules. Ada kotak. H. Hans rules. Okay. So all first. Salah. Okay. Lebih kotak. Okay. And this one. This one. And then this one. Remember, right? Okay. And then form what? This one. This one is the so lithium plus one S. Okay. This one is 2S. 2S already vacant. 2P also need 1S. 2S. 2P. Okay. Okay. Plus fluorine minus. Okay. So okay, so this one is full. The arrow should be inside. This one is not outside because it's difficult for me to.
Sorry, doctor, your voice is lagging, doctor.
Huh? Lagging? Is it lagging? How about this one? Is it okay? Is it okay?
Okay, doctor.
Okay.
Okay, doctor.
Okay. So please remember this one, the arrow, it should be not outside. It should be inside because actually it's difficult for me to write. This is not, the Webex is not similar with the Zoom. It can move this one. Okay, it's so difficult. I can move it, but using a Zoom is much user friendly. Okay. So remember this one, since or you already transfer the electron, so it's become this one, how many electrons? 2, 6, 7, 8, 9, 10. Okay. This one is for orbital diagram, and this one is Lewis dot, and this one in term of electron configuration. Okay. So you have to know this one. For example, this one 2sp. This one is already known. Okay. If for lithium, this one until 1s2 2s2. Okay, 2s2, is it 2s2? No, not 2s2. Okay, 2s1. Sorry, s2 s1. Okay, similarly, this one. Okay, you can do for the electron configuration. So you have to remember in three ways. You can present your interactions of the bonding, electron configuration, orbital diagrams, okay, as well as Lewis rules. Okay, so you have to remember this one. Okay, so this is the example problems. Okay, I want to see use partial diagram. Okay, uh, and Lewis symbol to depict the formation of Na plus and O2 minus ions from the atoms and determine the formula of the compound forms. Can you do? And then you paste your answer in the Padlets so that we can share together. You can share your answer. Okay, can you do now? Take one paper. This is a basic. I think all of you already know. If you don't know, you can refer to the what is it? To the web to the website or Google. Okay. Can you do now? You have the link, right, for the Padlet. Okay. Please refer to the chat box and then please post in the Padlet, and then I will see your answer. Okay. Use partial orbital diagrams and Lewis symbol. Orbital diagrams, remember, right? Lewis symbol. Can you do? I want to see, is it you still remember or understand? What have you learned? I think during when you take a organic class or during your secondary school, pre-university, during the matric, you still remember? I give you about 5 minutes. So before you start, maybe you have to know the what is it? The atomic number in term of in term of the electron configuration, for example, Na, right? This one, for Na. Okay, okay. So this one is 11, right? 1s2, 2s2, 2p6, 3s1. So 11. How about oxygen? Okay, 1s2, 2s2, 2p. Oh, okay. So please proceed. Use orbital diagram and Lewis symbol to depict the formation of Na plus and O2 minus ion from the atoms and determine the formula of the compound form. This is easy. Hope all of you know. Okay. Anyone already post in the Padlet? Okay, let's see. I share you. Okay, you didn't write your name? Better you write your name so that we can know. Okay, your friend already share. Okay, I share this one from the Padlet. Stop sharing. Okay, so Afif. Okay, Afif. So you use what method? Okay, so I just make it. Alamak, ini terpotong ke Afif? 1S2 to S2 to P6. Why until 2P6, Afif? Okay.
because it's NA plus.
To form NA plus. To form NA plus.
Go from
The formation,
NA11.
use orbital
Oh, okay,
diagram as a
okay.
symbol to depict the formation of Na plus and O2 minus ion from the atom. Right. So you have to understand the question. Okay. Okay, it's okay.
Sorry, doctor. Sorry,
It's
doctor.
okay. So you can do again. So that means from Na, bond together with oxygen to form Na plus and O2 and O2 minus. Okay. So I think even for me last time I'm quite confusing with the question actually. Yeah, it's okay. Anyone else can share? Anyone else by using orbital diagram?
Processing, doctor.
Huh?
Still doing.
Still doing. Okay, it's okay. No problem. Okay. Take your time. Actually, this chapter is very short. No problem. Tomorrow we can finish. Okay. I just want to see whether you still remember or you still understand. Oh, so difficult, right? Okay. So another 1 minute. I hope there's a one answer in the Padlet. It's okay. Afif is good. Good try. Okay. Okay, who's this? Okay, who's using?
That's the orbital. I mean the Lewis
Oh, you
structure.
use Lewis. Okay, that's good. So Lukman, is it? Lukman. Okay, Lukman. And A. Okay, that's good. Okay, two. And then, where's the result?
Oh yeah.
Yeah, where? Okay. It should be, there's an arrow for the result. Okay. There's a become cation ion. And then when we have another one. Yeah, this one, 1s, 2s, 2p, 3s1. Yes, good. So 3s1, it should be 2Na, isn't it? 2Na. So you should write here to 2Na. 2Na. Or you can make here like this. Okay. Or you can make another one. for Na. Okay.
Okay, okay.
Okay. So that this one go to this one. Okay. And then another one. Okay. This one. Sorry. I didn't put the arrow, but it's similar. Okay. The arrow is similar. Okay. So this one, the arrow is going here and the arrow is going here. Okay. This is good. Okay. Thank you very much. So I will post the answer. This one, this is my answer. Wait, okay. That's the, okay. So this is the answer. Okay. So if you look at here, this one right. If based on the orbital diagram, this is the first one, and this one based on the Lewis. Okay. Okay. Easy right? Okay. Thank you very much. Okay. So some of you still remember, but maybe confusing with the question. Okay. So let's we continue. Okay. Okay. So this is the example. So we already done. Okay. So in terms of arrangement of in ionic solid, actually we can present in terms of if we will more focus in chapter 3. I think chapter 3, whether in the face-centered qubit or cubic center arrangements. So it's okay. So this is the arrangement of the ion in ionic solids. Okay, but we will discuss later in chapter 3. So I don't need to explain more in this session. So for example, this one is a FCC, phase center cubic arrangement of the ion, and this one I think a phase center cubic because here there's a on the face of the what is it, the plane side. Okay, there's an atom here. Okay, and we can know the position of each atom when we discuss in chapter 3. Okay, so this is the arrangement of for the ionic solid. Okay, so as I told you that the size of the radii of the ionic compound is going to be decreased when transfer the electrons, and for the accepting the electron is going to be increased. Okay, so this is you have to know. Okay, so ionic bonds formations. Okay, due to the electrostatic attractions. Okay, the higher the electronegativity, okay, more than 2, so it can form the ionic bondings. Okay, what's else? This is because the opposite charge, okay, attract each other. Okay, the ions are stacked themselves in the crystal, okay, such as positive ions surrounded by negative ions, okay, or opposite. Okay, and then electrostatic force are non-directional. Okay, so you have to remember that. And cation to anion reduce ratio decrease. Okay, fewer anions can pack around the cations. Okay, so look at here that the bonding energies. Okay, the lattice energy decrease at the size of ion increase. Of course, because it's once the size is increased, there's no attraction. Okay, from the center. Okay, and the lattice energy increase significantly when ion involved have higher ionic charge. For example, +2 ions is higher. Okay, higher ionic charge compared to +1. Look at here. If we compare here, right? Lithium Cl and ACl. Okay, and ACl is the melting point is much greater. Okay, compared to LiCl. Lattice energy also. If you look at here that in kilojoule per mole. Okay, that means LiCl is much greater. Okay, in the lattice energy. Okay, Mg and Li, right? So if you look at here, they have a higher ionic charge. Mg 2 plus, Li is 1 plus. So that's why it's much higher, 3932 compared to lithium. Okay. Okay, so what is the properties of the material that have ionic bondings? Anyone can suggest what is the properties or the characteristic of the materials that have a ionic bonding? Anyone can answer? Or if you want to write in the Padlets or chat box, what is the characteristic or the properties of materials that have a ionic bonding?
High melting point.
High melting points. Okay, high melting points. What else? Anyone? I always hear a student from Indonesia. How about other country? Malaysian, there is a Malaysian or not? I'm not sure. Okay. What else? What is the characteristic? Why is melting point?
Because it's hard to break the bond.
Okay. How to break the bonds? What else? Anyone? Is it can conduct electricity or not? Anyone? Write in the chat box. Chemical inertness, yes, it's stable. Strong intermolecular force, yes. Electrical conductivity, okay. Nur Al Ain. Can you explain? Oh, cannot conduct electricity. Yes, cannot conduct electricity, but it can conduct electronegativity if it's in the melting form, okay, or dissolve, okay, or in the molten state. Okay, it can conduct electricity. But in solid state, we cannot conduct electricity. Okay. The material that can conduct the electricity is for only for the water. Yes, dissolve in water. Okay, it dissolve in water. Yes, some like salt, right? When we dissolve in water, it can conduct electricity. Okay. What else? Chemical inertness. Okay. So electric conductance, if we dissolve in water on the molten state, okay. In terms of the mechanical properties, okay, it's a brittle actually, okay, brittle, rigid or stiff, okay, fracture mechanism. That's the properties of the metal. Okay, good. Okay. So crystal-like structure, yes, crystal-like structure. Oh, this is the metal properties of. Just remember. Okay, you can read this one. Okay, so we finished about the ionic bondings. Any question about the ionic bondings? Is it right? Before we move to the covalent bond. If no questions about the ionic bonding, so we can move to the covalent bond. Okay, Afif had yes. Okay, so if there's no questions, then we move to the covalent bonding. Okay, so covalent bonds, a pair of electron share between two atoms in a molecule called a bonding pair or share pair. Okay, generally it's going to be share. It's not similar like the ionics. Okay, and you have to remember there's a non-polar covalent bonding, polar covalent bondings, high polar covalent bondings. So, for example, compounds that can have covalent bondings such as HH, HF, right? HCl. Okay. What else? CLCLs, CLCL, HH I think is a non-polar covalent bonding because the electron negativity is zero. Okay, non-polar. And then the electron negativity difference is just around 0.05. Is a really low polar. Okay. Okay. So occur between element is more different in electron negativity. This is what I told you. Okay. Okay. So I should have you have to highlight here. Small difference in electronegativity. And this is what I told you. Okay, usually close by in periodic tables, right? Okay, for examples, HH, Cl, Br, okay, occurs between non-metals, but can also occur in ionic and metallic solid. Okay, the class of sharing electrons, non-metal atom share outer s and p electrons. Okay, this one they share the electrons. Orbital overlaps. Okay, most common form of bonding found in nature is like hydrogen, yes, simple molecules. Okay, very strong bonds. Okay, just almost similar like the ionic bonding. Okay, so this is the examples. The simplest molecules, which is hydrogen, they share the 1s electrons. Okay, 1s1, this one also. So to form the hydrogen gas. Okay, bonding interaction overlapping. Okay, electron cloud. So that means this one actually the repulsion and attraction force is in equilibrium or similar. Okay, so that's why they can form the bondings in the equilibrium state. Okay, so how can we measure the bond length actually? Okay, so generally when the two atoms close together, okay, electron and the close nucleus repulsion becomes significant. Okay, become much closer. Okay, atoms repel against each other, and then repulsion force increase the system energy. So when the attraction force and the repulsion force is balanced, they are in equilibrium. So this is, we call it in equilibrium, this state. Okay. So at this state we can measure the bond length or bond ready. Okay. Generally, for example, we can measure for example HH. The data is already available in the handbooks. Okay, it's already available because they measure from the experimental. Okay, so from the average bonds energies determined or bond lengths, average bond lengths determined from the other compound, we can measure another bond length. Okay, for example, we have a data for the CC carbon. Okay, we have a data from the CC carbon. For example, this one, we have a data from the CC carbon. I think you can search in the internet. Okay, you can get the average bond length for each molecules. Okay, for example, CC. Um, the bond length is generally 154. Okay, and then CL. I think we cannot see this one. We can write here. Okay, okay, CC. Okay, bond length is 154. Okay, in ppm, in pm, picometer. Okay, and CL. Okay, so CLs we can get around 199. Okay, so if you want to measure like CL4. Okay, okay, so actually we can calculate based on this information. Okay, just based on the average. Okay, this one and this one, so we can calculate because this data is already available. Okay, we can predict actually. Okay, for examples, CCl4. Okay, and then if you want to calculate the bond between C to Cl, C to Cl, Cl, actually it's similar, right? Okay, so 154 plus, okay, 199 and divide by 2. Okay, so you can get around 177 picometer. Okay, it's almost close. Okay, not the error is very small. Okay, with the real one. Okay, so we can predict actually. Okay, that is how you calculate the bond ready or bond length. Okay, generally we will calculate or we measure, okay, during the equilibriums, because after the repulsions between the atoms, okay, the length is going to be increased. Okay, the answer calculations are related to bond length. The common bond length will be provided, or we have to Google them. Actually, is we not cover in this chapter. Okay, it's just additional knowledge. Okay, the calculation of the bond length. Okay, if you learn about the quantum, yes, the information of average energy as well as the bond length is important. Okay, but yeah, you can search. Okay, average energies, average bond length, for example LCL, HH, okay, BR, okay, SIH is available in the website, any website. So you can try by yourself to calculate, for example, bonding CO2, right? Okay, just find bond CC and OO, and then you can get the average bond length for CO. Okay, something like that. It's just additional, because last time I teach a quantum, so I still remember about how to calculate the bond rating. Okay, so let's see the distribution of the electron density in hydrogen. If you look at here, that the same distance, okay, between attraction and repulsion is in equilibrium. Okay, so electron density is high around and between the nuclei. So this one, and that's why the electron negativity is 0, or between 0 to 0.5. We call it as a non-polar bonding, non-polar covalent bonding. Okay, so this is in terms of hydrogen. Okay, other diatomic molecules such as Cl2, O2, N2 is also covalent bonding. Okay, by sharing their electrons. Okay, so this is another one. Okay, for O2. Okay, to oxygen. This one in terms of neon configuration, OO. Okay, generally for the bond lengths of the triple bonds, double bonds. Okay, triple bond is much shorter than double bond, and double bond is much shorter uh, uh, single bond. Okay, so you have to remember that. And triple bond is more stronger than double bond. Double bond is stronger than a single bond. Okay, this is the basic that you have to know. Okay, okay. Is what is it? 450. We try to finish a covalent bonding. Okay, so non-polar versus the polar covalent bonds. Okay, this is what I told you. Pure covalent bondings. Okay, or non-polar. Okay, look at here. Okay, 0.520, no dipole. Okay, this is what I told you. Atom are share bonding electron equally. Okay, for example, hydrogen, nitrogen, and F2. Okay, so and then polar covalent bondings. Okay, polar is a 0.5 to 2.0. Okay, so this is what we call as a unequal sharing. For example, HBr. Okay, 0.7. This one is high polar, HF, because the electronegativity different. Okay, how can we calculate the electronegativity difference? Okay, you have to refer to the predictables. Okay, and this one 3.1, right? The electronegativity difference. This is ionics because more than 2. Okay, so the range is going to be 0.0 to 0.5. Okay, 0.5 to 0.522. Okay, and 2.0 above. This is ionic. Okay, so you have to remember this one. Okay, so pure ionics, see, just like a touch. Okay, and this one is polar. Okay, and pure covalent. This one pure ionic is just a transfer, right? Something like a touch because it's transfer the electron. This one is a Vischer. Okay, there's a difference here. So if you look at here, that the arrow, right? The arrow is to the right side because this one is more electronegativity than this one. This one is positive. So the polar arrow points towards the more electronegativity different. Okay. So for examples, what else? NH, right? Look at here, NH. Okay. Okay. NH. So this one is delta plus, delta minus. So the polar should be, the arrow should be like this. Okay. You understand, right? Okay. So this is the boundary. Okay. You can refer. Look at here that mostly covalent, polar covalent, and mostly ionic. Okay. So some information they suggest between 0.4 to 1.7, okay, but it's almost average, okay, to 0.52 until 3 or more, okay. Okay, so this is the electron density distributions, okay, the comparison between the pure non-polar as well as the polar. You can hear that this one, right? Okay, it's toward the electron, the more negative, okay. F is not equal, okay, this is much higher, but this one is equal, this one is equal, okay, understand, right? Okay, so bond length, bond order, and bond energy, if you get here, as I told you, okay, bond order, the number share electron pairs, okay, and bond energy is required to overcome the attraction force. Is it how much energy we can introduce to the molecules that we can break the bond actually. Okay, bond length is the distance. Okay, the relationship between bond order, bond length, and bond energy, we can hear that. See, this one, triple bond, double bond, and single bond. Okay, so more energy if you want to break the triple bond rather than single and double bond. Okay, and the bond length you can hear is very short. Okay, because it is reasonable, right? Okay. Okay. Any question about that one? About the covalent bondings? Okay. So as I told you, how can we calculate the electron negativity? Electron negativity. Okay. This is you have to know how to calculate the electron negativity difference. Okay. So for examples, hydrogens. Okay. Equal to you can Google actually 2.1 the electron negativity, and Br is equal to 2.8. Okay. So when they form a bond, covalent bond, okay, so it's going to be here. Okay, so to see is it is covalent bonding or not, okay, this one is Br. Br. So to see is it electronegativity how much, 2.8 minus 2.1, okay, so is equal to 0.7, okay, so actually is more than 0.5. So this is polar covalent bonding, okay, because it's more than 0.5. Okay, okay, is it right? This is how you calculate the electronegativity difference. Any questions about the electronegativity difference? Okay, okay, so this is the covalent bondings in the diagram, orbital diagram. Okay, this is in terms of ground state. Actually, I will not explain in terms of what is the ground state. Is the lowest energy they can form. Okay, is more related to the quantums. And some special cases there is a hybridization actually. Okay, there's some bonding form. Okay, sp3 orbitals. Okay, so can you do this one? Use a polar arrow. I think it's before we finish our class. Okay, can you do for A? Use a polar arrow to indicate the polarity of each bond, and then you post in the Padlet before we stop our class. A, only A. How you show the polar arrow? NH, Fn, and ICR to see the electronegativity. And then you post in the Padlet. Do A. Not this one. There is a 2A, right? This one it should be. This one it should be. Okay, not this one. Can you do? The arrow indicate the polarity. How to use the polar arrow? This is the polar arrow. Okay. NH, FN, and ICR. Please give me the answer in the Padlet. You have 4 minutes before we stop. Nobody? Post in the Padlet? I'm waiting.
Sekejap doktor.
Kejap Okay.
Yeah.
Where's the Padlet? Okay. So tak ada jawapan, tak boleh balik. Tak boleh keluar. Okay. There's one here, anonymous. It's okay lah, anonymous. Wow. What's your answer? NH. Not like this. It should be like this. Okay. There should be a link. Okay. This one you should be for NH. H. Okay. So N. So delta plus delta minus arrow should be not in the middle. Okay. Okay. Understand? Okay. So should be there's this one. Bond. Okay. Okay. Good. Okay. Who else? Okay. This one. This is just the normal arrow, not the polar arrow. Okay. Should be. Yes, here you have to remember. There's this one. Okay. D minus D plus D minus D plus. Okay. This one 2CL. This one the correct one. Okay. Okay. D plus. Okay. I have to remember this one. Okay, let's see. Okay, I think that is enough. Anyone else? Anyone else? Okay, this one. Lamia. Okay, Lamia. Upside down. Upside down is quite good. It's okay? Upside down. Okay. Lamia also should be there's a plus minus like this. Okay? Everything is okay. Should be at okay. Okay, good. Okay. So thank you very much. Okay, do not forget the arrow. Okay. It's different like a normal arrow. It should be like this. Okay. And must be there's a delta plus and delta minus. Okay. Thank you. So before we stop, Any questions? Already for 1 minute. Oh no, 4. No. Any question? Sorry, doctor. Wait, doctor. Sorry, doctor. It's okay. Okay. I think it's good. Okay. Everybody is participant. Okay. So if you have no question, we stop our class today and we will finish our what's this? Okay, this one is correct. Yeah, this one is good. So we come to Zafran. Zafran is answer is correct. We continue for tomorrow. We will finish this chapter by tomorrow. Don't worry. Okay, and then I will give you the assignment. Okay. You have no questions, so we end our class today. Thank you very much, guys. Okay. So we stop here. Thank you, guys.
Thank you,
Thank you,
Doctor.
Doctor.
Okay.
Thank you, Doctor.
Okay.